Good morning to all. This is Dr. M. Vairalashmi, working as Assistant Professor of Chemistry, VSEPR College for Women, Virudhunagar. I am here to discuss about the VSEPR theory from chemical bonding. First, what is VSEPR theory? It stands for valence shell electron pair repulsion theory. Okay, why do we need to study this theory? You remember in the Lewis dot structure, Lewis was not able to expand the shapes of molecules. But this theory is important. It is used to predict the shape of any given molecule. Okay, so the name itself refers what a theory is. So it refers valence shell electron pair repulsion. Okay, so you consider an atom which is made up of nucleus and so many electrons. The electron which is present in the inner orbitals are called intervening electrons or interlining electrons. If this atom is going to make a bond with some other atom, it will not use the intervening electrons because these intervening electrons are simply seated electrons. These electrons are held together by the nucleus, so they are having more attraction towards the nucleus. So they are not involved in the bond formation with some other atom. Okay, this theory says if this atom is going to make a bond with some other atom, it will use only the valence electron. Okay, so the valence electron is present in the valence shell. So the valence electron is of further two types. One is lone pair of electrons and the another one is bond pair of electrons. So the bonding electron pairs are rigid and they are localized, but in case of lone pair of electrons, they are delocalized. Okay, I will explain this localization and delocalization concept with an example. Now you consider the water molecule addition having 6 valence electrons. Out of 6 electrons, 2 will be used in the formation with 2 different hydrogen atoms. Okay, so these are bonding electrons. These two are the bonding electron pairs. These electrons are held together by the 2 different atoms. That is oxygen and hydrogen. So they are held together by 2 parent atoms. So they are highly rigid. They are not free to move. So they are localized electrons. But in case of lone pair of electrons, they are held only by the single parent atom, that is oxygen. So they are free to move, they are trying to expand more. So due to this expansion, lone pair of electrons are repel more than the bond pair of electron. So lone pair repel more. Okay, so in case of bond pair, there is also repulsion. The bond pair repulsion is minimum than that of lone pair. Okay, so what about the lone pair bond pair repulsion? That is intermediate between the lone pair and bond pair. Okay, so the order of repulsion is lone pair repel more than the lone pair, which repel more than the bond pair. Okay, so this is all about the past slides of VSEPR theory. Now I will give you one formula which is used to predict the shape of any given molecule. Okay. The formula is steric number, that is equal to half into number of valence electron of central atom plus number of atoms attached by sigma bond plus or minus charge. Okay, what is plus or minus charge? If you consider the atom CO3 2 minus, that molecule CO3 having 2 minus charge. Okay, so we can apply this molecule in the formula as CO3 2 minus, so we can put as 2 plus. Okay, consider an atom NH4 plus, the NH4 molecule having plus charge. So we are mentioning it in the formula as minus. Okay, so minus becomes plus, plus becomes minus. Okay, so now we can see some examples. The first compound is beryllium hydride. The electronic configuration of beryllium is 2, 2. So the steric number, that is equal to half into number of valence electron of central atom of beryllium is 2. Okay, so what is central atom? So the atom which is a bigger one is called central atom. if the two atoms are in similar size, the atom which are having less electronegativity is called the central atom. Okay, so the number of valence electron of central atom is 2 plus the number of atom attached by the sigma bond is 2 because there are two hydrogen atoms. So the steric number is equal to 2. If the steric number is 2, the hybridization will be sp hybridization. Okay, so 1 is 1p, so that is 2. If the steric number is 2, we are getting sp hybridization. Okay, so if the hybridization is sp, the geometry of the molecule will be linear. Okay, so the bond angle between the two bonds, BH bonds will be 180 degree. Okay, so by using this VSEPR theory, we can predict the geometry and also bond angle. Okay, what is bond angle? It is a bond angle between the two bonds. It's called the bond angle. Okay, and also we can predict the hybridization pattern. Okay, the hybridization of pattern of this beryllium hydride is sp. Okay, so we can see another example. Boron trifluoride B of 3. So the electronic configuration of boron is 2, 3. The steric number is equal to half into valence electron. Valence electron of central atom is 3 plus number of atom attached by the sigma bond is also 3. So the steric number is equal to 3. If the steric number increases by 1, hybridization is also increases. So there is a sp2 hybridization. Okay, 1 is 2p. So the total is 3. So the steric number is also 3. Okay, if the hybridization is sp2, the geometry of the molecule is trigonal planar. So we are getting trigonal, geometry of this molecule is trigonal planar. Okay, what about the bond angle? The bond angle between the bonds will be 120 degree. So each bonds are situated at an angle of 120. Okay, let us move on to the next molecule, CH4. Okay, so the electronic configuration of carbon is 2, 4. So the steric number is equal to half into valence electron of central atom is 4 plus there are 4 atoms are attached by carbon, so that is also 4. So the steric number is also 4. So here the steric number is increased by 1. So the hybridization will be sp3 hybridization. So what about the geometry? The geometry will be tetrahedral. Okay, so what about the bond angle? The bond angle between the CH bonds are 109 degree 28 centigrade. Okay, so the next molecule is NH3. It is very important molecule. The electronic configuration of nitrogen is 2, 5. The steric number is equal to half into valence electron of nitrogen is 5 and plus number of atom attached by sigma bond is 3. So the total 4. The steric number is equal to 4. If the steric number is 4, we are predicting the hybridization as sp3. Okay, but here there is only 3 hydrogen atoms are there. So the bonding electrons are 3. So the other will be lone pair of electrons. Okay, so we expect this molecule is tetrahedral geometry, but this is not so because of lone pair of electrons. Okay, so here there is one lone pair of electron on the nitrogen atom. Okay, this lone pair of electron repel the bonding pairs. So these lone pair repel the these two bonding pairs. So due to this repulsion, the hydrogen atom come close to each other. So this will cause the geometry change. That is, the tetrahedral geometry is changed into the pyramidal geometry. So we look the molecule on the nitrogen atom, on the periphery of the nitrogen atom, it looks like pyramidal geometry. So we are getting pyramidal geometry due to this lone pair of electrons. So this lone pair repel the bonding pairs. So due to this repulsion, we are getting pyramidal geometry. Okay, so what about the bond angle? Here the bond angle is 107 degree. In case of CH4 molecule, the bond angle is 109 degree 28 centigrade. So here there is a reduction in the bond angle. This is due to the repulsion of the lone pair of electrons. Okay, so let us move on to the next molecule. What are here? The central atom is addition. Electronic configuration is 2, 6. Steric number is equal to half into valence electron of oxygen is 6 plus there are 2 hydrogen atoms are there, so 6 plus 2, so the steric number is equal to 4. So here there are 2 atoms attached to the oxygen, so the bonding pairs are 2. Obviously there are 2 lone pair of electrons. So if the steric number is 4, so we can predict the hybridization as sp3. So we can expect the geometry of this molecule as tetrahedron, but this is not so because of 2 lone pair of electron. So these 2 lone pair of electron present on the oxygen atom, so they repel more. So in case of methane, there is only 1 lone pair of electron, but here there are 2 lone pair of electron and oxygen atom. So here there are 2 type of repulsion, lone pair and also lone pair bond pair repulsion. So due to this repulsion, the bond angle is further reduced to 104.5 degree. So obviously the shape of this water molecule is V shape. So we can look the structure of this molecule on the periphery of the oxygen atom. It looks like the bend shape or V shape. Okay. So the next molecule is BCl5. So the electronic configuration of phosphorus is 2, 8, 5. Okay. So the steric number is equal to valence electron of central atom 5 plus there are 5 atoms attached by the sigma bond. So the steric number is also 5. Okay. So here there are 5 atoms, so the bonding electron pairs are 5. There is no lone pair of electron, so the hybridization will be sp3d. So here the steric number is increased by 1, so the hybridization will be sp3d. Okay. So what will be the structure of this molecule? It has trigonal pyramidal geometry. So it has trigonal pyramidal geometry. Okay. So the next molecule is SF4. So the central atom is sulfur, the electronic configuration is 2, 8, 6, the steric number that is equal to half into 6, that is valence electron of sulfur is 6 plus there are 4 fluorine atoms, so 4 that is equal to 5, the steric number is equal to 5, it means the hybridization will be sp3d. So we can expect the geometry of this molecule is trigonal pyramidal. Okay, but here there is 1 lone pair of electron. There is 1 lone pair of electron which is present on the sulfur atom. Okay, so to predict the geometry of this compound, we can use the another one rule, that is Benz rule. So according to Benz rule, in the trigonal pyramidal geometry, the lone pair of electron goes to the equatorial position, whereas the highly electronegative atom goes to the axial position. Okay, so this is Benz rule. So here by using this rule we can predict the geometry of this molecule. Okay, here there is 1 lone pair of electron on the sulfur atom. So according to Benz rule, it occupies the equatorial position. Okay, so here it occupies the equatorial position. Okay, here there are 2 repulsion, that is lone pair bond pair repulsion of 2 lone pair fluorine atoms. So due to this repulsion, the structure of this molecule is further reduced to seesaw structure. So you look, this is a seesaw. Here the lone pair is there on the sulfur atom and 4 fluorine atoms are attached bottom of this seesaw. Okay, so this compound looks like seesaw. Okay, so the next molecule is ClF3. Okay, so the central atom is chlorine. The electronic configuration is 2, 8, 7. The steric number is equal to half into the valence electron of chlorine is 7 plus there are 3 fluorine atoms. The steric number is equal to 5. If steric number is 5, the hybridization will be sp3d. So we can expect the geometry as trigonal pyramidal geometry. But here there are 2 lone pair of electrons. So due to this 2 lone pairs, you are getting only T shape. Okay, so according to Benz rule, these lone pair occupies the equatorial position. So you see this is a T-shaped structure. Okay, so the structure of this molecule is T-shaped. Okay, so let us move on to the next molecule, SF6. Okay, so the central atom is sulfur. The electronic configuration is 2, 8, 6. The steric number is equal to half into valence electron of sulfur is 6 plus there are 6 fluorine atoms. So the steric number is equal to 6. Here the steric number is increased by 1. So the hybridization will be sp3d2. Okay. So here there are 6 fluorine atoms. So the bonding electron pairs are 6. There is no lone pair of electrons. So the lone pair is equal to 0. So the hybridization is sp3d2. You are getting octahedral geometry. Okay. So here this is an octahedral molecule. In this case, these bonds are not equatorial and these bonds are not axial. So all the bonds in the octahedrals are equal. Okay, so here we can now use the Benz rule. Okay, you just remember Benz rule is only applicable to trigonal bipyramidal geometry, not for all others. Okay, by using this way, you can predict the shape of any given molecule. Thank you.